screen. Cool. Well, I guess happy Monday. I haven't been here in a little while, speaking in front of you. Last week, I guess it was, no, we did jQuery, right? Quickly kind of snuck in there. Same thing's going to happen tomorrow. I'll come in and talk about connects, but in the morning you'll have, I think, maybe Chrome again, talking about SQL, how to use SQL in applications, which is kind of fun. So that tells us that there's actually about 2 days worth of SQL time. And even, I'd say maybe a day and a half. Today we'll use SQL, and then we'll, tomorrow we'll learn how to include that in our applications. But then pretty quickly we move into an abstraction called connects. So tomorrow afternoon we'll start to write queries using a library called connects. And it's just a different way to do this. You're going to find that there's actually a lot of ways to wrap this language up in more of a Ruby or JavaScript style programming language or pattern. But today we want to learn how this language works, because no matter how we wrap it up with other languages, with other frameworks, underneath it's still the same thing. And if we understand the thing underneath, then we can use the abstraction much better. So SQL, this is the language we're going to use, the structured query language, to make queries to a database. Data is the most important part of any product. It's hard to argue that it isn't. So the example that I heard Don give when he was doing the same presentation, imagine if you're Facebook, and one day someone comes in and they wipe out your entire code repo, all of your user interface, and your backend completely gone. And for some reason you had no backups, so you don't have this. So you have to start over and write this from scratch. Is this something that Facebook could recover from? With their engineering talent, the amount of software developers they have, the amount of money they have, right? That is a recoverable problem. Likely it'll never happen, but they could recover from it. Now imagine the same thing happens to their data, the databases that hold all their customer information, all of your information. Let's say they lose that and there's no backup. How long does it take for them to recover from that issue? I would say that's an unrecoverable. Facebook is not coming back from that. They are their data. That is why Facebook is as valuable as they are today. So these databases are very important, very useful. The SQL gives us a window into the data that we're talking about here. And I'm going to kind of go through, talk about how we persist data. I know that last week with Mongo that got brought up a little bit. And then how we can start to design databases for our use, for our web application use. And then how we can query into those databases. And that's what the whole day is going to be about. This afternoon we'll go into some more complicated queries. We'll write some 6 or 10 line queries, I guess, right? That sounds like quite a bit, but we'll work up to it, right? That's how this language is learned. We work up to it. And I think my main goal today is to show you that the stuff that we do in SQL belongs in SQL, and it doesn't belong in JavaScript. So I hope this becomes a bit more clear. What I find is some people they're learning 2 languages now, JavaScript and SQL. I already know more about JavaScript, so maybe I'm more comfortable with that. So maybe I'll do a lot of the stuff that I should actually do in SQL with JavaScript instead. I'm going to show you some examples of why that might be a bad decision. Okay. So data persistence, this is a problem that we're trying to solve now. Last Thursday, we solved this using the MongoDB, and it was pretty kind of interesting, right? You just take these JSON objects or documents, put them into a database, and then grab them again, query based on certain information inside of there, or even the ID of it, if you know what that is. So we can, if let's say our route has a user ID, we can grab that user's information from the database based on that ID. So these are 3 formats. When we store data, an important thing we need to do is give that data context. We don't just take a big chunk of text and throw it into a database, because then we don't know what that text means. Is that someone's name? Is it a blog post? Is it just the subject for the blog? We don't know. And so what we have to do is give it a little bit of context. Here are some different formats, file formats that we've used in the past for this. Maybe not you directly, but in web development. So CSV stands for comma-separated values. This is a tabular data format, right? We have at the top, we would have maybe the names of the columns, and then under that, each entry would be a row of data separated by commas to indicate where the actual columns are split. So we could take that, throw into Excel, and see a spreadsheet based on that if we wanted to. And the context that we're giving it is this rows separated by new lines, and columns separated by commas. Does that make sense? We don't really use that much. I mean, in some applications it makes sense. You can export from one tool and import that CSV file into Excel. That's can be pretty useful. But for web development, although there are lots of CSV libraries out there in JavaScript, we don't tend to use it very often. I would say JSON is the more common one for us to use. It has dominated web development. And XML was sort of the original web development file format for storing data like this. So we won't get into XML because it's not really, it looks a lot like HTML. You can name the tags yourself if you want. JSON came out on top, so that's where we're going to spend most of our effort in learning. And I kind of want to show you a quick example, although this might not be super valuable if you've talked about this before with Garrett. So I've got this section in here called persist. And the whole idea is this thing here is it's a web server. It's just an Express web server. We import some libraries. I've got this little helper function here that takes in like a JSON, maybe an object, and it stringifies it for me and returns the stringified version of that. So that could be kind of useful. I've got this reference to a database here. So this is really just a path to a database called students.json. So I'm going to store this file right next to my expressserver.js, right next to my index.js, whatever the files that are in there. I'm just going to create a file called students.json. Okay. If that file does not exist, then I will create it. And how I do that, it's kind of interesting. I open it and then I close it. And that's kind of a quick way to do that in JavaScript in Node. Is just you open the file and close the file, and that creates it for you. The reason I want to do that is because I don't really want to. I want to make sure that I can read that file every time I start the server up. This is actually a prerequisite to persistent data, right? The problem with TinyApp is every time you shut the server down, we lost our in-memory database. So now what we need to do is make it so that every time something changes, we save this file to our local machine. And then when we start our server up, it reads that file, brings in the latest information, and then we continue adding to that, saving to that. And if we bring the server down and we come back, we're back to where we left off, right? This is what we get. This is how we get that. Every single time this server loads, every time we start this application, it does a file system read file on that database file right there. And it takes the result, which we expect to be an array of objects, each representing a student. Cool. We convert that into JavaScript with the parse command. We also, well, I'm using a body parser for JSON, so I can add body data. Now I've said, instead of URL encoded, I used .json here. It's just because I'm using a different format. When I send data on the body of my request, I'm going to send it as JSON rather than this URL encoded key 1 equals label 1, or key 1 equals value 1, and key 2 equals value 2, and key that type of thing. I'm not going to do that this time, but that's why we would use URL encoded here instead, right? We have seen body parser. Okay, good. So you've got these two routes here. One for get. I can get the root, and what that does is it sends me back a pretty version of that students array. Or I could post to the students route, and this will create a new object. If the student's length is greater than 0, well then we will take that last ID and just add on to it. Kind of a naive way to do that, but we need unique IDs. So this will work fine for this application. Name, email, phone, etc. We push that onto the array, and then we write that file, and then we serve the response. So we do not serve the response until that file has been written back to the server. Okay. So if we run this, and I go to my site, localhost 3000, we can see here, empty array of data. Right? Now I need to make a request to this server, and I don't have an interface, a user interface. So what I'm going to use curl. I've got this little curl command here, curl-h content type. So I had to set a header. I had to tell it that I'm sending JSON to it. So the body parser will parse that JSON for me. -x post, so I'm setting the method as a post request. So it looks like this is going to make a post request to the /students route. Great. And then here's a big chunk of data that I'm going to send it. A new student named Baxter Asserby. with an email and a phone number. Sound good? So I will take this. I'll open up another terminal here, and I'll paste that. And I've just run this command, and what I got back was a, a 201 created. That's what my response came back as, 201 created, powered by Express. But here we go. This is the record that was created. This is Baxter's record ID number 1. Okay. So now when I reload this page, there's Baxter. And I kill the server, and I bring it back, and I reload, and Baxter's still there. And this is the whole point of this, right? So I can make this request many times. I can say over and over. And when I do that, it updates my store. I reload, and I get multiple entries for that user. Kill the server, bring it back, come back. I've still got my data. So what are some of the, why don't we just do it this way? It's relatively easy, right? I don't have to do any, I didn't have to do any database queries. It's just, I'm just saving my student data into this file over here. But what are some of the issues that we might come across if we're doing it this way? Size of the file, yeah. So, and it's plain text, which is, yeah, so that could be bigger in size as well. So that file can grow in size. Also, it might get slower and slower to load, right? Can we think of some other stuff? Can you do data analytics? I mean, yeah, I guess you're right. Well, if the data's there, I can load that data. Then I can do a bunch of JavaScript that might do some analytics on that data, right? But with SQL, that can be a lot easier. And that's actually one of the points I want to make is that sometimes we take that data into JavaScript, and then we do stuff with it. We loop over it, and we create new arrays, and we try and create some new, maybe some analytics from that. But with SQL, we could just make the queries that might give us that response back, and so that might be more useful. I think it is. Having that language rather than just that language that's specific for it. It's a domain-specific language to database queries. I think that's the strength of it. There is one major issue with doing it this way. It has to do with writing the file. So with a web server, if I make a request and or I make a request and it saves that file, no problem. I make a request and someone else makes a request at the exact, around the same time as me, and we're both trying to save this file at the same time. Who saves first? How does that work? Does one save and then the other save, and the first person's data gets lost? This is the problem with this strategy, is that we can have one sort of write to a file. It's mutually exclusive, right? We can't have all these requests all causing file writes like that. We'd have to make sure they happen in the right order so that the person who saved first, their entry gets in, and then the person who saved second, their entry is in after that one. So there are 2 entries at that point. And we don't have that here. But there's actually a pretty straightforward solution if we want to save JSON documents safely. Do we know what that is? You've already used it. On Thursday. Mongo, yeah. So this is what Mongo does for us. Is it saves these JSON documents like I just did, but it does it in a way where it can save them atomically. It can save them in a way that we will retain the data integrity, right? So Mongo helps us with this. If we want us to be storing JSON documents, Mongo is a pretty good solution for that. Okay. Make sense? One more thing I forgot that I wanted to mention here. Let's go back to this quickly. Yeah, I just want to talk a little bit about the model that we're going to be dealing with today, because one of the relational databases. This is why we're here today. We're going to learn about SQL, but before we learn about SQL, we have to learn about relational databases, because relational databases, it's an approach to storing data. It's been around for 50 years. It's well proven. It's ubiquitous, right? This is what some people will use Mongo for sure, without a doubt, but it's new. Relational databases, that design's been around forever. Here are some of the benefits. This is why we want to use relational databases. We want to reduce the duplication of data. This is a really important part of using relational databases. This helps us out. Anytime we have duplicate data within a database, we now have to manage that data as it is duplicated. So let's say that we have, actually I'm going to show you some examples of that because it's easier when we see the examples. So I'm going to call out when we're reducing the duplication of data. But this is one of our primary goals using a relational database. We also want this robust query language. Having access to SQL is a strength of relational databases. And although at first it's quite confusing, it's different than what we're used to. At the end, when I watch people who are really good at this, they do things really quickly that I can't dream of. So it's inspiring. It makes me want to learn to do this language much better. And as a result, I feel like I'm definitely stronger in that. So the third thing we want to do with relational databases is accurately model reality. So the reality that we're going to model today and what we're going to be using as our example is the reality that you've been in, that you are in right now. It's the boot camp reality. It's a cohort has many students. A student creates assistance requests. A student submits assignments. There are many assignments that you could submit. We tie those students and assignments together. We tie teachers and students together through assistance requests. So this is the model, the reality that we're going to model today. Sound good? When it comes to database design, there's a lot we're going to have to consider. So we're going to kind of step through that. The first thing is this whole idea of reducing duplicate data. And the way we do that is through data normalization. First, I'm showing you database denormalization, or a duplicated or denormalized database would look like this. Could someone tell me what's wrong with it? With this table? This is how we store data in a relational database, in tables like this. Of course, yeah. I've got duplicate data. And I said we want to avoid that, right? We want to remove duplicate data from our database. This is reduce the duplication of data. Primary goal. And here we have April 9th, April 9th, April 9th, April 9th. So my example for you of why we want to do this, why we don't want to store multiple data, because we have to keep track of it then, is my application now has to, let's say, week 3, you come and do your town hall. And as a result, we also have this tradition where now that you've been together for a little while, you get to come up with a group cohort name. And that cohort name would then be applied in the database for you, and you'd see that throughout whatever the material is, right? Does that kind of, I know we don't do that, but let's say that happened. In that case, we would then have to go and make a database update. And we'd have to go through here, and for every student in the database for that cohort, change the cohort name. So instead of just changing it in one place, we're changing it for 14 students, let's say, right? That's kind of a problem, because we have to keep track of that. We have to write code against that, and we could have bugs around that. So one of the ways we can solve that is by normalizing our database. And so what we do here instead is we break this out into 2 concepts, students and cohorts, right? And now every student still belongs to a cohort. It's just that that cohort has an ID that does not change, and that cohort, we reference them in that cohort instead. So all the information about the cohort is tied to that cohort ID, and the student is tied to that cohort ID. And the cohort ID will not change, but the data around it may change. So the name of the cohort could change, no problem. Malloy Jenkins, Maximilian, and Pegasus, great names, I guess. They're all random, by the way. I didn't come up with these. I go to random name generators, and I leave out, like, I don't know, maybe the slightly risky racist ones. It's tough sometimes. You can never tell. These ones look okay, but I guess what I'm saying is you got to be careful with randomly generated data. You never know what could come out of that, right? So here I've done this. My 3 students, they just point to cohort 3. That happens to be named April 09. And if we renamed that, then those 3 students have a different cohort name, no problem. We only had to change one entry in the database. And this is how we reduce the duplication, is by splitting this up into different tables. OK. Now we have to come up with a way to design these things that are going to grow in complexity. You don't have to read this. It's OK. If you can't see it, this is just sort of imagery. This is what an ERD looks like. We're going to go through and draw one of these ourselves. I've got one, and I've also got some examples of one. It's just a way for us to, maybe in discussion with our group, maybe I have an idea for a database. I want to share it with someone. Best way for me to do that is to draw it out, tell them which tables I want to use, what columns those tables will have in them, and how these tables are linked together through different keys, OK? So we'll go through a tool to do this, and I will zoom in and kind of show you what these tables look like. When we do this, we want to keep in mind, And I'm going to show you this convention because when we're learning new stuff is kind of hard to kind of know where to start. Like, oh, where do I sit down and I have to start. Okay, so you might start like, well, how do I name this table? I'll just tell you. Figure out sort of the theme of the table. Is it students or cohorts? Pluralize that name. Just always pluralize it. And use snake case. So this is what snake case looks like. Lowercase letters, underscores instead of spaces. Does that make sense? This is what it would look like. A table. Students, not student. It represents many students. So there's lots of rows. Each one represents a student. So we'll call it the students table. There's no capitalization, as you can see. The reason I'm telling you this is now you don't have to think about what sort of a naming convention you use. I'm just going to tell you what to use. And then as you're more comfortable with this, feel free to come up with your own. That's fine, but not until after the midterm, right? This way people can also predict what these things are called to some level. Every table is going to have something called a primary key. This is a unique identifier for every single row so that we can make sure that these rows are actually unique rows. Even if every single other piece of data in that row is the same as another row, that unique identifier should be different. Okay. We'll call that ID all the time. I'm not going to call that student underscore ID. It's in the students table. There's no point in prefixing it with students underscore. I see that a lot, though. And it's OK, but it's kind of redundant. When we get into disambiguation near the end of this lecture, you'll kind of see why it feels redundant. Okay. And then you get to decide. Here's where you have some freedom. Names, column names, name, email, start underscore date, end underscore date. These are all column names that I've decided for a student. Do these ones make sense? There could be more as well. I couldn't fit them on the slide, right? GitHub, phone number, whatever. We put all that stuff in there. And then near the end, we've got this other one here called cohort underscore ID. And this is a foreign key. This is how we map to another table. When I say a cohort has many students, the way that we know which cohort a student belongs to is is in that row for that student, we reference back to a cohort ID. Does this make sense? Yeah? Okay. This is very important. The foreign key is on the many side of the relationship. When you're drawing these things, you can use the tool that I'm going to show you. That's fine. It's not my recommended way. My recommended way is a whiteboard. Find that to be a lot easier. We draw these things on a whiteboard or a piece of paper. And then we link them together. And we have to figure out first which side is the many side of the relationship, so we can put the foreign key on that side. And when we do that, we link them together with this other little symbol here. It's like three, they call it a crow's foot, I believe. One to many, right? It's like this kind of thing. So we put one to many. The cohort ID tells us what cohort this student belongs to. This is the many side of the relationship. There are many students, many side, foreign key on this side. Cool? I sometimes come up and I do a review of an ERD. It's no big deal. The only thing wrong with them usually is that the foreign key's on the wrong side. That's why I'm doing this here. That's why I'm telling you 3 times. Okay. We also have this other concept called join tables. And this is what occurs when you have a few foreign keys. Because we might actually have relationships many to many. So one to many is more common, but many to many is also common. So in our reality, boot camp, there are many, many relationships. A student can create many assistance requests, right, throughout their whole time here. You don't just get one. That would be unfortunate if you only had one assist. Can you imagine? What would you save it for? You don't even know, right? So you get many assistance requests. And as a result, a teacher, a mentor, someone else, will respond to many assistance requests. And they might be many different students. They might be all from the same student. But the many, many relationship that we're talking about here is many students to many teachers, right? And the way that we link students and teachers together is through assistance requests, if we think about it. Cool? So this join table, we're going to name it assistance requests. And it's we're going to have a couple foreign keys on there. There's going to be a student ID foreign key. There's going to be teacher ID foreign key. And whenever a student creates an assistance request, their student ID is going to go in there. And then when a teacher accepts an assistance request, their ID would go in there. Now they are mapped together. We'll identify when it was created. So when it was created would be when the student first actually asked for assistance. When the assistance request was actually started is when the teacher accepts it. And then when it is completed is when the teacher finishes it off, ends the assistance, right? So there's these 3 pieces of temporal data here that we're keeping. Time-based data associated with that assistance request. Why would I keep those 3 things? Do I care about that as an educator? As an administrator of Lighthouse Labs? I think so. I can find out how long it took for a student to get help, and I can find out how long they were being helped for, right? Those are things I can find out from this data. And so it's not just that I link students and teachers together. It's also that I apply a little bit of very important information, some metadata about that relationship, right? I've got here student rating, teacher rating. When I'm done an assistance request with you, I think you get to choose some ducks. How well did it go, right? So we might put that there with it as well. Tie that together, right? See how well the teachers are doing with their help. Same with students. We come back, say, is the student slightly behind, on track, ahead? Do they need some stretch work? So we might tie one of those ratings there as well. Sound good? Any questions about this? Okay. I have assignment ID in there as well. If you make an assistance request, sometimes it's based on an assignment you're currently working on. So we could put that in there as well. What's kind of cool about that is I might be able to figure out which assignments have the most assistance requests associated with them. And if I can figure out which assignments are having the most assistance requests, I can make some good decisions about which assignments are maybe more complicated or less clear. That's actually what I'd be looking for. Which are people asking for a lot of help because the assignment is just not clear? I'd put a bunch of other stuff in here. Your feedback, the little bit of text that you put in when you're asking for help. We'd put all that into this table. Right? All right. So I'm going to go use a tool called draw.io. And this tool is very frustrating for people to use at first. It was for me. When I watched this lecture, David also, who used to lecture here, he hates it. I'm going to, I guess, tell you some of the things that I found when I was using it that made it easier. But this is the reason that I prefer to use a whiteboard or a piece of paper. Just this tool kind of can get in your way. Okay. So draw.io, there is a link to it in my notes. And along the left side here are a bunch of different little tools that we can use to draw diagrams out with. And the one we're curious about today is entity relation. Because we're making an entity relationship diagram, so it makes sense that we'd want to be using these little widgets for an entity relation. All right. I've also got, so I've got lots of options over here to describe my tables. Here's one right here. That could be very useful, right? Although, as far as I'm concerned, they call these things rows, but what I know about database tables, those are actually the column names. So I don't know what they're doing with that. Don't let that get in your way. Come over here, check this one out. This is cool. Has a primary key. And I know I need one of those on every single table. So this is the one I want to use. This one here, it's too complicated. We don't need to deal with this kind of PK, FK thing that's going on here. It's only day one, right? So here's where this is what we're going to use for all of our tables. I'm going to drag this thing over onto the stage here, and I'm going to give it a name, students. A cohort has many students, so that's what I'm going to start with. I guess this could be cohorts first. Either way, you just got to start with something, right? So here's my cohorts table. Following convention already. The name of the primary key is going to be ID. Just do that the same every time. That's easy. And then what's some of the data that we would put on a cohort? Right. What about, now here's where I told you I'd help. If I hit tab, it's actually tabbing through these. And I know I can click on this, but I find that tab, if I switch to the keyboard with some of this stuff, it's a little bit easier. I can move with up and down. I can move this stuff around. And I know that for me, dragging and kind of finding the right place to put it, it can be kind of frustrating. So keep in mind there are some keyboard shortcuts for some of these things. I also want a start date and an end date. So I was able just to submit and then tab to the next thing. I can hit delete to get rid of that. I don't know why they put like this like half-length thing at the bottom there. I just get rid of it all the time. So now here's my first table. Cohorts table, name, start date, and end date. I'm going to take this whole table, I don't know how, I guess by selecting the gray part at the top, and I'm going to use the shortcut Command D for duplicate. So I've duplicated this table now, and I want this to be the students table. So students have a name. They also have a start and an end date. If I choose this column here, I guess any of them really, and I hit Command D, it's going to duplicate that for me. So that's good. I can add new columns that way. Start date, name, email, GitHub, phone number, all that stuff. And then I want the start date. I kind of like these things to be down at the end. My dates, kind of like them to be at the end. So I've moved those down with the keyboard arrows. Oops. Name. Oh, I deleted it. Get rid of that. Oops. There we go. Good. So name, email, GitHub, phone, start date. I'm missing one thing here, at least. One very important thing. Cohort ID. And again, it's the cohort ID is on the students table, right? Because there are many students. So a cohort has many students. The way that I say what cohort the student belongs to is the cohort. I point to the cohorts table with an ID. Now the reason why we don't just create a column here called students and then make that an array is because they don't exist in SQL. We can't just make an array. I can't put multiple students in here. So that's why I have to put the foreign key on the many side of the relationship. That's an early break. Okay, well, I'm not going to take their, still got lots to go through. So here, cohorts ID. This is convention. Name of the other table underscore the key name, the primary key name. So with our convention, if we're naming all of our primary keys ID, then it's very straightforward. We identify what the other table is, underscore ID, no problem, we're done. And then I'm just going to go in here and put FK just to indicate that that's my foreign key. Not required, but it kind of helps out. All right, step 2 to this entity relationship stuff. I've got my tables. I've also got down here a bunch of options for little crow's feet things, little linker things, all different symbols. We can see 1 to 1, many to many, with 0 to 1, just different, all these different things that indicate 1 to many. This is what we want right here. This is many, I guess they've called it. Many. That's all we need to use. I don't need to use any of these other ones right now. I don't need to be that specific with the databases we're creating. We're web developers. We don't need to do a ton of crazy databases. So we'll just limit it to this many thing here. And we drag this over. This is where things get really kind of frustrating because dragging this thing, you want to make sure you choose this blue dot. And when you drag it over here, you're linking it up to a green dot. Right? If I don't choose that green dot, it's going to kind of just link to the side of it. But I want to link to this foreign key here. I'm making it green dot. I select, OK, good. Now when I move this around, it comes with me. Okay. I take the other side of this, looking for that green dot in here. Click it. Good. Now these things are linked together. Cool? OK, so a cohort has many students. Do we want some more practice drawing these tables out? A little bit? OK. So we also talked about, well, I'm going to actually show you what we want to come up with at the end here, just to see where else we want to talk, where else we want to kind of spend some time. I've got this bootcamp PNG file here. So we have students and cohorts. Name, age. I didn't put age in ours. It doesn't really matter. But this is a good way to find out, too. Like, as you're looking at this on the board, you start to think, okay, well, what are some of the queries that I want to do? Let me find the average age for the students in the program. Maybe that's something that I need. Okay, well, my database structure doesn't support that, so I should go back, add that in here. I just duplicate the thing, call it age, and then I can move it up. Right? Make sense? Cool. All right. Let's create this join table here. So I'm going to create a new table, but I'll start by duplicating one that exists. I'll drag this down over here, and I'll call this assistance requests. And assistance requests, I just want to delete all this stuff. I guess I got to shift click to delete all that. So an assistance request, there's what sort of information is on assistance requests. We want to know who the student is that created the assistance request. That's going to be a foreign key. We want the teacher who's responding to it. Well, that already tells me I need another table, right? So maybe I should duplicate this table, bring it down here, just add it while I'm thinking about it. A teacher has a name, a start date, and an end date. Maybe also is active flag or something like that. And so that just says, are they actually working this month or not? So, and then they also have a start and end date, when they started working here, when they actually ceased employment here, which is kind of different. We wouldn't necessarily put the end date if they were just taking a break. Might just put inactive, right, instead. So what other stuff do we want to put on this assistance request? A description, great. Let's do that, yeah. So don't need a foreign key for that. Oops. So that description of the problem, description. No, is that right? Thank you. Wow. Okay, description. Anything else? Yeah. So yeah, we want to know when it was created. I would say we'll create the assistance request at that point. So I'd say created at something like that maybe, or created date. A lot of times with these tables, people will actually put a created at and updated at field for every single table, so that we know when that row was created and then also when it was last changed. And another thing we might do is actually added a deleted at column, because we might actually want to delete that row. We might want to keep the row, but indicate that it was removed. So we just put deleted at, and then we look for things that were deleted at before this time, right? Okay, so created at makes sense. There's also a little bit more information we want. We want to do a started at, so this is when the teacher sits down, and then also a completed at. Anything else we want to put on here? Assignment, yeah. So the assignment ID might be useful. We tie that here. We say assignment ID. But what this means is I also need a new table, right? Assignments. And my assignments are going to have a name, maybe content, and also a duration or something like that. Now, I could put more on these things. As it comes to you, just add it. Ask questions of each other. Take your requirements. I mean, we've got some user stories on this board right here. If I were to take these user stories and say, can I accomplish this user story with the schema that I have right now? Yes or no. If you can't, then add more to it, right? But do it in the design phase. Don't wait until all those tables are there, because it's a lot harder to add columns later on. You can do it, but it's just, you'll find out it doesn't work, right? So I'm going to grab one of these little crow's feet here, drag it down, and I've got to link these tables together. I'm going to take the students table here. Oops, that's the many side, so I'm going to actually go the other way. Oh, this is going to be real fun, isn't it? There we go. Now this thing's in the way, right? This thing's not going the way that I want it to. And it took me a little while to figure it out, but it's this tool up here that helps me with that. So I can switch this over to this kind of a thing. And actually if I, oops, I guess, I can actually get this going on, or I can kind of drag this and make it fit around. Right. But I had to make sure that I activate that functionality with that little tool. Okay? If your lines aren't behaving, this stuff up here, this thing helps quite a bit. I also need to make a link between my teachers. Oh, so what I'll do is I'll just make a straight line in between them because it's actually pretty close to each other, right? And then also my assignments need to have a link as well. And then that one can go back to being something like that. I don't really like that. I don't like these straight lines. I like to go. Okay. How do we feel now? Process. So this is the process. We'll practice it today. We're going to learn all about the Navy, and we're going to review. Everyone's going to get a review on their ERD. It's a very important part of this to get the feedback on that. Okay. So we'll move on from that. Let me just show you the rest of this stuff here. So students, assistance requests, cohorts, and then we have assignments over here. Assignment submissions are what ties students and assignments together, so it's another join table, right? 2 foreign keys, a many-to-many relationship. There are many assignments. A student does many assignments, and assignments are done by many students. And this is how we signify that. Could someone tell me, maybe, we're noticing there's some actual duplication in the column names, right? I have a column name over here called duration for assignments, and I have a column name over here called duration for assignment submissions. Do those mean the same thing? No. So it's okay. If two tables have the same column name, it's okay. Even if they do mean the same thing, but they don't contain the same data, that's okay. Name kind of means the same thing as we move it around different tables. But you don't have to say student underscore name in the students table. That's also redundant. Right? So in the context of the assignments table, what does duration mean? That's average time it takes, yeah. Our estimate, right? When you see that estimate, that would be our estimate. The submissions here, that's when you actually put in the time. We'll record how long you said it took, which is important to us. And actually, we have the estimates in there, and you get those estimates. But what would be great is after 6 months or something like that, we switch over and start to use not estimates anymore, but an average of the duration that students actually took. That would be kind of cool, right? So in that way, this is kind of maybe a way you do that. We still estimate every assignment that has a duration, but later on we could potentially just average out the duration for that assignment amongst all the submissions. Cool? All right. So we'll just finish off the last little bit about schema, and then we'll take our break. We've identified the names of the tables, all the columns inside of it, which ones are primary keys, which ones are foreign keys. We also have to consider data types. Data types don't necessarily go onto our ERD, but when we create the table, we do have to identify what the type of what data type that column holds. It's very important. Here are some examples of some data types that we can use. The most common ones at the top: integer, any number we want to put in. It's a pretty good, not literally any number, but for the most part, when we want to store a number, integer is a good column type for that. We've got char and varchar. So char is, we're able to indicate that it's between 1 and 256 characters, basically. That's our limit, is 256 characters on that. And if we use char rather than varchar, we're saying that it is always the same amount. So it might be good for a postal code. That could be an okay thing to store in there. They're all the same length. Whereas varchar, if something, we can set the maximum length, but it could be shorter easily if we want, right? And it'll kind of scale up for that. So no point. We don't worry about space in databases as much as we used to 20 years ago, when gigabytes were tens of thousands of dollars, right? We don't care as much anymore. So a lot of the stuff about choosing the right data type, where it used to be about conserving space and size, when we're introducing SQL, we don't concern ourselves with that. It's just not something we need to think about today. So we want to choose the right data type for the data we're storing in there. And we're going to learn how to do that. But if we have to go with one bigger just to be safe, like something that's going to take more space just to be safe, let's do that. It's OK these days. Date, very specific data type. What do we think we want to store in there? Right? Start date, end date, that type of stuff. Text. Text would be like full blog posts, megabytes of data if you want. That's what we would put into text. Or another one would be a blob, binary large object, blob. Text or blob, depends kind of what you're storing in there. Use text more often. Like if you're making a new blog for yourself, a blog that stores large, I guess, posts, you'd put that into a text field. That would be your data type for that blog entry. Even if it was Markdown. If it's Markdown that you're writing, store that Markdown in a text column. I'm not sure what the upper limit is, but the docs would probably tell us that. Boolean. Boolean is just true or false value. So my teacher is active column would be a Boolean data type, and we just say true or false for that. And then I've called out a few other ones here, small int, big int, and serial. We'll talk about small int and big int, but serial is a special type of number. And the reason why it's special is because it auto-increments, and it is, I guess, increments in a serial fashion. So it's first value is 1. You add a new row in there. Now the value is 2, and then add 3, then 4. So it's going to increment serially. And this is really good for our primary key ID. That's what we kind of want for a primary key. We want it to take care of that for ourselves. And what a serial number does is, let's say we have an empty table. We add our new entry. The ID becomes 1. We add a second entry. The ID becomes 2. Third one, it becomes 3. We remove the second one. We delete the second one. There's only 2 entries in our database. When we add a new column in there, or a new row, it becomes 4. It doesn't care that 2 is available again. Even though it's available again, we don't use it. It was used already. It's already been used once. We don't get to use it again. And so serial enforces that for us. Does that make sense? I recommend making all your primary keys serial, at least at the beginning here, for your midterms for sure. Cool? Small integer, small int, big int, and regular integer. There is a difference between these. And it has to do with how much, the size of the number that they can store. So a small int can store anything between negative 32,767 and 32,767, plus or minus. So if the number is 12 or 15 or 82 and never can be higher than that, you could use small int if you want. But remember I said you don't have to worry about space saving. But that's kind of why it's like this, is that it takes more space to store a integer than a small int. And so if you had millions and millions of rows, then that might start to add up to be megabytes and megabytes and megabytes, right? Let's say. And that's why they have it this way. Integer, for most numbers, no problem, but we do need to be careful. There are some numbers that go outside of the boundary of what an integer can store. An integer can store up to over 4 billion values, but we're going from negative to positive, so we actually have about 2.1 billion. Does anybody know about Gangnam Style? Have anyone seen the video on YouTube? There was a time when Gangnam Style broke YouTube and broke their view counter. Does anybody remember this happening? Sorry, vaguely, yeah. And it's because it went over 2.1 billion views, or over this limit here. They stored the number of views of a video as an integer. As soon as it went past that 2.14 whatever billion value, it couldn't be stored anymore. Maybe it starts back at 0. Maybe it just kind of, not a number. Who knows the exact how it's going to result in the interface when we actually see it there? But they needed to upgrade this column to a 64-bit big int instead, so they could store 9 quintillion value, you know, that kind of, or whatever that number is. I'm not even going to bother, but this is a massive number, and this is what we'd have to use now to store YouTube views instead, right? They just switch, and you can do that after. 10 years later, if you want, you can change a column type to become a bigger number. Basecamp, anyone heard of Basecamp? This is Ruby on Rails. Anyone heard of Ruby on Rails? Yes, Ruby on Rails. So the inventors of Ruby on Rails have a company called Basecamp. They used to be called 37 Signals. Recently, they admitted that they made a pretty big mistake, and one of their columns was an integer, not a big int, and their servers were down for about 10 hours or whatever as a result of that. So they had to do a large database migration to switch that column or that to be a big int instead. So so that it could store all the values it needed to. Make sense? Kind of, somewhat? Okay. We've also got this ISO 8601 format. It's just a fancy way of saying we have a standard way to indicate the formatting of a date. Here we're indicating that this is the April 26, 2018. That would be 9:36, 28 seconds. 0 time zone, so UTC. I've got all the information I need in here to give you a date and time, sort of anywhere, I guess on the planet, or I guess anywhere with any time zone, right? This is how we'd store dates, or this is how we tell the database what date we want to use. It's not actually how they store them. We don't store dates as a string like this. We store them as a date object or as a date type. But the way that we tell the database what date we want to add in is like with a format like this, so it knows what we're actually saying when we give it a string like this. Cool? Okay. Phone numbers. This one's fun. Is there any difference between, well, except for there is one different one, right? Maybe these two are different. But for the most part, phone numbers could be described in many different ways. I actually had so my partner was ordering something this morning. He said, I need you to come fix this form again. And so she was trying to submit. And every time she did the reCAPTCHA and then she hit the submit button, it would take you back up to the phone number thing. And all it would say is, please fill this out in the format that's required. She's like, and she tried, and she had brackets around it, and she had dashes in there, and she tried a whole bunch of different things. She couldn't get it working. So I right-click, open the inspector, and I take a look at the field. And it's supposed to be a telephone type. And there's a regular expression in there that tells me exactly what it has to match. And the way that they ultimately ended up forcing us to put the number in there was like, that was what the regular expression had to match for it to work. It's stupid, right? But maybe they didn't want to, maybe they wanted all of their numbers to go into the database the exact same way. I think that's a reasonable thing to want, but I don't think that's the right way to get there. So here's a whole bunch of different ways that I could describe a number. I should be able to accept any of these ways in my form field, and then when I take this, I should then convert it maybe into only numbers, put that into my database, right? Make sense? So I would strip all the characters, put that in, and now I've got numbers. Now, but there's a problem with this. What sort of data type do I use to store a phone number? Text, and like specifically the one called text. You're on the right track. It's just that text would probably be too big for it, because text could hold multiple megabytes of blog posts, for example. So it might not be the best for a phone number, but I'd say varchar is a good option. We do want to store this as a string, right? Because there's a few different reasons. If we choose integer, that's good. It'll work up till, but numbers that start with a 3 or a 4 or a 5 won't fit. We can see right here that a number that starts with an 8 is over 8 billion, so that won't fit as an integer, so we'd have to use big int. Okay, well, let's use big int instead. Another problem. Has anyone seen a phone number that starts with a 0? Maybe, right? I maybe in Europe. I know in Europe I've seen it, but if I'm going to store a number that starts with a 0 in a database, I can't use an integer value because it will chop those leading zeros off of it for me. and then my number's wrong. So for phone numbers, let's store those as strings, as varchar. Varchar 32, varchar 64, something that'll give us enough space to store a phone number in there. Make sense? Okay, so last thing before we take our break, I'm just going to show you sort of, there's sort of a write-up about this stuff, data types. We have to really consider which data type to use. And, so here's an example. Storing, when you store currency, we don't store dollars. We store cents. So if something is $1, we store it as 100 cents because we do not want to lose any precision. Floating point numbers, numbers with decimals in them, they have a certain level of precision, and if we try and add them together, we might drop a little bit of that precision. So instead what we do is we would store them as integers, but as cents. So $1 is 100 cents. That makes some sense, right? I didn't do that on purpose. What about a bank account, though? Now I want to store how much money someone has in their bank account, and I need to store the value in cents. Could I use an integer for that? I guess I could. The problem is, if I store, you could have maybe up to 21 million in your account as a result of that or something, right? Not a problem for any of us. But there are people who would be pretty pissed off if they put 25 billion in and lost, or 25 million in and lost 4 million as a result of it just not being able to store that number, right? So in that case, for bank balances, I would 100% use big int for all of those, just to be safe, right? Because I know I have to store them as cents. So in addition, here's this page, falsehoods programmers believe about names, and it just kind of indicates that we don't know shit about anything, right? Like this is, people have exactly one full name. No, not true. People's names do not change. Not true. So let's not make any of these assumptions when we're designing our database, right? Let's go take a look at these lists and see all these things that people have come up with over these multiple years of experience of building these databases. Here, let's not assume that all names are written in ASCII. This is a format that wouldn't support like foreign characters, perhaps, right? Or international characters. What about people's names are not written in all caps? Yeah, that's up to you. Basically, the way that it goes is whatever you want to call yourself, that's your name, so all bets are off, right? There's another one of these right here. This is a list of other resources. Awesome falsehood. Tells us falsehoods, things we believe to be true about pretty much everything out there that we have to write software around. So some of those things, like for example, nowadays, does it make sense for us to create a gender column or like a male column? Is male true or false? Not anymore, right? And even before that would have been shitty. But 50 years ago when databases were designed, that's the way people thought, right? So we want to be building out our database schema to match the world we live in today. And that means we need to learn about all these things that we thought were true that might not be true. Might need to have support for multiple gender, for example, right? There's lots of stuff in here. I haven't read a lot of it, but it's a good reference, okay? All right. When we get back, we'll talk about indexing. And let's take a 5-10 minute break and then do that. No questions, though, right? We're good? Screen. Awesome. All right. So we've got there's a good point brought up by Abby. You're going to notice that I actually here for students and cohorts, I have the same. I have I have a start date and an end date column for my students, and I have a start date and end date column for my cohorts. And so that could be duplicate data. Like we think when a cohort starts, when a student starts, they start in a cohort. And when they finish, they've graduated and that cohort has ended. So we could just map those students' start and end dates to the cohort they belong to, right? But the reality that we know here is that although that's mostly the case, it's not 100% of the case. So we might actually have to have students have their own start and end date. And any student that does not have an end date, they're still in the program. And every student who has an end date, they have finished the program. And their start date, it could match the cohort they're in right now, or it could match the cohort from the previous cohort. There's lots of reasons why this could be different. So just, although we want to reduce the duplication of the same data, like exactly the same data, when we have these concepts that are across these tables like this, I do still think it's valid for a student to have their own start and end date and a cohort to have their own start and end date. I think that's okay to split it up like that. Make sense? Cool. That's a good question though, because if removing duplicate data is our primary focus, then we think we get rid of some of the columns that store that duplicate data, and that's really what we want to do, except for the times when it actually means something a bit different. All right, we're back from break, so we should be nice and fresh, ready. We walked around, we got our drinks, right? So we're going to talk about this concept which transcends databases. And it makes sense to bring it up today, but this is a programming concept that I want you to take with you for the rest of your lives. Does that sound important? Okay. So let's forget about databases for a little bit, and we'll just think about JavaScript again. And we'll think about how we indexing, this process we can use in development. So I've got two data structures here, right? And they store the same data, but in different ways. What is the difference between the two of these things? One's an array, one is an object. Great. They are different data structures. So let's say that I have the ID of one of my users, and the ID is RTWJ0V. Cool? I want to now look inside in that first array. I want to find the user's name for the ID RTWJ0V. What do I need to do in order to find that user's name? How do I find that name in the array? Sorry? I loop over the array, yeah. And then on every iteration, I look for the ID, and if I find that ID, I've got the name. That's right. There's fast ways to do this. We can use the find method. We could actually do the loop ourselves and do the logic ourselves. But the point here is that we have to iterate over and look through potentially every single item in the array to find that ID. And if we get all the way to the end and we didn't find that ID, that user's not in there. And if we only had to search for the first two, let's say, and then we find it, we don't have to go look at the rest of the array. We already found that ID. So we have this idea of a best case and a worst case. The best case is it finds it in the first iteration, and the worst case is that it has to go all the way to the end, but usually it's somewhere in the middle there, right? Yeah. Do you want to have a comment? No, it's good. Okay, so any clarity on that? We're good? If next week you'll get into some computer science stuff, we'll talk a little bit about computational complexity, big O notation. But what we'll say here is this is a linear search, and it takes linear time. And the linear time goes up based on the number of items that are in the array. Bigger arrays take longer to search through than smaller arrays. Does that all make sense? All right. Second data structure. If I have the ID RTWJ0V and I want to find the user's name for that, how do I do that? Just direct object lookup. And this takes constant time. So the difference between linear and constant time is that in linear time, the size of the array matters, and in constant time, the size of this object does not matter. It doesn't matter if it's 50,000 items. If I know the ID, I can just get it. I can just do that lookup and get it in constant time. But if I'm having to search through an array, I have to search through 50,000 values potentially. So this is the difference between these two data structures. And what I've done is I took that first data structure, that student's array, and I looped through it once, and I created an index out of it. And the index is how I'm able to quickly find the values that match that ID. This is how Google search makes things fast. Anytime someone says I indexed it, yeah, they're just going through that page, finding the words that are in there, and then using that as the search term so they can do a constant time lookup to find that word that you're searching for against the document that belongs to that, right? Databases use this. This is why I'm bringing it up today. That foreign key, or that primary key that we're creating, that auto-incrementing serial value, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc., that value is indexed. If I want to go and look into a table with a whole bunch of rows in it for that value, I do not need to search for the ID. It's indexed already. I just find it in constant time. Okay? But if I need to search based on name, I'm actually looking through every row. Cool? This is the limits we need to understand right now for this. We don't need to even use it in our databases today or next week or for our final projects. But one of the things we might do is say, well, I'm doing a lot of lookups on this table for this type of column. I'm going to index on this column, and what it does is it creates like a duplication of this data, and we trade space for speed. We give some space to create the index. That's what this is, right? We have to create this object now. So we give up some space, but we get speed back. And so whenever we index a column in a database, it's going to take up a bit more space, but we're going to get a much faster query as a result of that. Does that make sense? We don't need to know how to do it, though. We just need to know that this is ultimately where we get to when we make databases fast. Cool? All right, back to databases now and talking about queries. So I've got this thing running. We'll get rid of that. PSQL. This is the command we're going to use to run our database software, PSQL. PSQL-V, PSQL, let's see. What's the version thing? Like, can I just find the version of this or something? -V, capital V, that's why. So, PSQL-V. I'm using Postgres 10.4. I've got a database here already. If I want, I can connect to my base, my first database, which is called Postgres. Everyone should have a database called Postgres already. And if I create new databases, the way that I do that is I first connect to the Postgres database. So I connect to that. I can do \L for a list of all the databases that are currently in my relational database install. Got a lot of tables here. The one that I'm actually interested in today is called W4D1. So I'm going to connect to that. A few different ways to do that. PSQL, W4D1 will connect to it automatically. We can see over here, I'm connected to the W4D1 database. If I connect to Postgres first, I'm connected to the Postgres database, and I want to connect to my W4D1, \C, W4D1. Hit enter. Now I'm connected to that database instead. If I just type in PSQL, it's not going to work for me, but it's going to work just fine for you. I run this. It says database K Jensen does not exist. I didn't tell it what my database is, so it assumed that it was the same as my username. In the virtual machine, what's your username? Everybody know? It's Vagrant. Vagrant is your username. There's also a database called Vagrant in your Postgres install. So if you type in PSQL, you're going to connect to that Vagrant database. But if you type in PSQL, or then you can create any database you want and connect to it just like I did. That's fine. All right, so I don't have a K Jensen database. That's no problem. I'm going to connect to W4D1, and I'm going to describe the tables. Looks like I've already got this database in here. And if I select star from students, here's a whole bunch of students. 192 of them in this. So I can make my queries in here. I can insert, I can select, I can do all that. I can list all the databases, list all the tables. So a pretty useful tool. Make sense? All right. You'll get practice with that today. All right, so I want to create a new, let's say that I've created my database, which I actually didn't really show you. I'll show you how to create a database as well. So I will first connect to my Postgres database, because that's the one that gets installed with my Postgres install. And now I need to create a database, create database. W4D1, live, whatever. I can use underscores. So I've just created that. Oh, something went wrong there. It didn't actually do it for me, but I want you to keep your eye on this right here. What's the difference between those two lines? Yeah, so when I'm able to start putting in a query, it'll have an equal sign. But if I have not finished my query yet and I've hit enter, it's going to allow me to do multi-line queries this way. And so normally what happens is people say, it doesn't run my query. We do not put the semicolon, that's why. I need a semicolon to end this query. So I can actually, I'm on the next line. I could, well, I don't have any more to write on this query, so I can just end it like that. Put the semicolon, hit enter. Now I got what I expected, which was create database. And I'm back to an equal symbol down there instead. So I could start to run my queries. I guess what I want to do is connect to that. Now I'm connected to that database. Now I could run any of these queries that I'm talking about. Okay. This is how I create a table. I've got my ERD, so it's actually pretty straightforward. I know what the names of the columns are. So I can put those in my list here. Create table, give it the name. Then I put parentheses around it. Comma separated list of columns. Here's how I'm creating my primary key serial ID. ID, serial, primary key. These are all sort of constraints that I'm putting on this as well. I'm saying that it cannot be null. That the ID cannot be a null value. That's very important to me. So I've put a constraint on it right here. The name also cannot be a null value. So I put a constraint on that. I said, if someone tries to put in a row with an empty name, don't let them. The database is actually pretty strict about this. We've got the start date and end date. Either of those could be null for whatever reason. I would say for students, the end date would be null because until they finish, we don't put an end date in there for you. Yeah, make sense, kind of. Okay. This is how we're going to create those foreign key references. For my foreign key, I'm going to say that I have a cohort ID. The data type is integer. It's not serial. If I made it serial, then it's also going to increment itself, and that's not what we want, right? We just want to be able to put a number in there that points to something that auto-incremented, not actually have it auto-increment as well. That's why the foreign key does not match the data type. It is not serial like it was here. But it's an integer, and so a serial and an integer, those two data types match in the size that they support, so that's okay. I also have big serial and big integer if I needed to use those two, but I'd want to use both of those two together. So my cohort ID is an integer that references another table called cohorts and a column in there called ID. And then I got this thing on here called onDelete cascade, which is really going to throw a wrench in things. I don't need that, but it's very useful for me, especially during development. Whenever I create a reference like this, let's say that I have a table for students and a table for cohorts. And I add a bunch of students that belong to a cohort. And then for some reason I delete that cohort. Can those students still point to that deleted cohort? They can't. We don't want that to happen. We don't want that cohort to be empty for them. So what we would do is we want to maybe remove those students or switch them to another cohort, right? In this case, let's say that we just remove the students when their cohort is deleted. Like we would never do this, but this is an example of how cascade works. We say here, onDelete cascade, so when the cohort row is deleted, it will go into the students table, find all the students that belong to that cohort, and also delete them as well. Otherwise, you're going to get a message back that says, you know, can't delete this cohort because you've got students that point to it already. It's a constraint. They'll use the term constraint. The foreign key constraint prevents you from deleting those relationships. By setting up this delete cascade, which you'll see in my examples, it's just easier. What you could do alternatively is delete those students first and then delete the cohort they belong to. That would be okay. But as soon as we try and delete a row that has something referencing it, the constraint prevents that from happening. Okay? So we got this concept of CRUD that we've been bringing up every now and then. Lectures, interviews, whatever, some of the assignment material. Our database queries kind of map pretty well to the CRUD style updates stuff that we're doing. So when we want to create something, usually it's an insert into the database. When we want to read some data, it's a select. And then when we update or delete, we'll use the same term in SQL for that, update and delete. And this is kind of what it would look like if I wanted to insert one item into the database. I would insert into the cohorts table a number of different columns. You'll notice I don't have the word ID here, because I don't set the ID, right? How does the ID get increased? It's serial, exactly, so I don't need to worry about that. So I will say that I do not have a value for the ID. That's up to you. But I do have a value for the name. I have a value for the start date, and I have a value for the end date. So we'll list those out, and then we'll say here are the values, and we'll list them out in the same order. This is important. The columns and the values, they need to be in the same order so they match up, although they don't need to be in the same order that they actually were created in. As long as the name and name match and start date and end date, as long as those match, we're okay. That's how we're telling it what to put into what column. Then there's a situation where we want to actually insert many things at the same time. In that case, I'm actually still deciding what columns I want to insert for, but I have a comma separated list of value sets, basically. It's always better to use one query instead of 4. It's always better to use one query instead of 50, right? I mean 4 instead of 52. But the fewer the better. That's how we make our databases faster, is just the fewer queries that we do. So if we're going to insert 4 things at the same time, it's better to do it as one query like this. Okay? It'll be faster. So that's really quick on inserts. You'll spend some time on this. Where I want to spend most of my time is the most complicated part of SQL, which is the select, from, where, by, order by, whatever, right? It's these things here, these 6 sort of clauses that we have for a reading or select query. This is where we want it. I think this is where most of the complexity lies. All right. So I've got my data set. This is not real data. The database is not even the same as what's on Compass. I just kind of took a look at it and then made something a bit simpler for us. They have like 100 tables in Compass. It's quite big. The data is not real. It's all random generated. No privacy concerns here. Also, just so you know, the date range for this set is actually February 12th, 2018 until the 1st of January 2019. So we're coming up pretty close to that date. But I kind of just like made it into the future when I did it. So what we have to imagine is today is January 1st, 2019. If we're working with this data set, imagine that is the current date. All right. So select star from students is going to give us all the columns, all of the rows for all the students in that table. I think that's pretty straightforward. Probably in the weekend material we learned that, right? Good. Now we can also be very kind of specific about which columns we care about, and this is useful for just limiting the amount of data that we're retrieving. We want the ID, the name, and the cohort ID from students. We don't care about the start date, so it doesn't include that, right? Here we're leaving out columns. That's the purpose of this. All right. Now this is where it starts to get a bit more confusing. I think these 2 queries are pretty straightforward, right? This one. When I made this first selection here, or either of these selections, how many rows do I have? Let's say this is all the students that came back. There's nothing hidden from us. How many do I have? 12. Good. So how many students do I have? 12 total. So when I want to count those, I get 12. It's taking all those rows and then crunching into one value for me. This is called an aggregate function. Taking a row set and aggregating it into one value. Count is a good one. Average would work for this. Max or min would tell us the min or max of any of the values in that column. These are aggregate functions. Those are some examples of that. We'll use count for this, because count's a good way for us to find out how many students are in the entire program. Right? We don't care which cohort they belong to in this case. So we're just doing select star from students, get them all, but when we wrap this in an aggregate function, collapses that back for one value, we get a count of 12. Cool? Now, slightly different, we put a where clause. Now we care about the cohort, and we want to find out how many students there are in cohort number 3. So here we say select, we could just start out with select star from students where cohort ID equals 3. That would give us back 1, 2, 3, 4, 5 results. I can see right here. And then if we just do that count aggregate again, collapse that back into one value, the count is 5. There are 5 students in cohort number 3. Good? All right, we'll keep building on this. Now, instead of just for one cohort, I want to know how many students are in each cohort. This is probably the most confusing part of select, is group by. If I look at this, and I want to group by their cohort ID, how many groups do I have? Yeah. I have 1 student in cohort 1, 2 in cohort 2, 5 in cohort 3, and 4 in cohort 4. So I have 4 groups of students. So when it groups this, it actually creates 4 different groups. But those 4 groups have multiple rows in them, right? Imagine we have 4 buckets. 1 for cohort 1, 1 for cohort 2, 1 for cohort 3, 1 for cohort 4. And as we find these students in this, we put those in each bucket. Now we have these buckets. We can count how many students are in each bucket using that aggregate function again. So here we're getting each cohort and the number of students in each cohort, and that's a good use of the group by clause. Is that kind of, I know it won't fully make sense right now. Kind of confusing. But think about it. Whenever we do an aggregate function, we're taking a whole bunch of results and breaking it down into one value. And when we group by, we're bucketing things, and then we have multiple groups, multiple rows. And for each of those, we can collapse them back down to one value. And that's how we end up with 4 rows here. We had 4 groups, and so we have 4 results. Make sense? Yeah? All right. Now what I'm doing, so I've added group by. We've used where in the past, right? This is actually a filter sort of what we're doing in our query. We only have row results where the cohort ID is equal to 3. In this case, we're using something called having, which is different than where. Having is used after we've done the all the grouping and the filtering and all that. So here, the first thing we're going to do that same query, and we're going to get a result set of 4. We're going to get 4 results back: the cohort ID and the number of students in that cohort ID. We can do further filtering using the having clause. Now that we have these 4 groups, we can filter anyone who anything does not have greater than or equal to 2 students in it. So we're going to get rid of that first cohort using the having clause. And having count ID greater than or equal to 2, that makes some sense, has to happen after the query is done. So you'll use both where and having for different things. And the whole point is that they happen at different points in the query. One happens early on and one happens at the end. Filter early, filter late. Where, having, right? You can also add order by. Order by count ID descending. Okay, yeah, I want the most students first and then the least students last. And we can add a where back in there. Where students who started after April 1st, 2018. So now we have 2 results for that. It left out, so how this is going to work is it's going to take all 12 students, and it's going to filter out any students who started after April 1st, 2018. So we minimize the results, the query now. So now it only has the students from here down. We filtered out these sets already with the where clause. This is all we have now. We take this and we group this. Sorry, no, this one, I guess, right? We take this and we group this into 2 groups, 5 and 4 students in each, and we order by descending here, so we get 5 and 4. Okay. So the where and the having happen at different times, as I kind of showed. In this one, actually, it's interesting because the having is kind of useless. I just noticed that. My initial where clause gets rid of this person in the beginning. So there is no cohort that has fewer than 2 students in it. So that having is actually redundant here. I'd probably come up with a better example for that. Cool? Does that kind of make sense, though? We've used all 6 here. Okay. We'll want to practice the group by. You'll want to ask for help on that. It didn't make a ton of sense to me before I prepared this lecture, and now I feel so much more confident about it. So, okay. So why did I put a little fire beside update and delete? Yeah, cautious. Fire burns, and so does update and delete. What does the first query do? Yeah, everyone's password becomes the same now. Yeah. I mean, there's hashing and all that kind of stuff that goes on, but yeah, you just want to be careful of this type of thing because that would update everybody's user to have the same password. And even if it was update user set name equals Karl, then everyone's now named Karl, right? And I don't wish that on anyone. So we want to be careful of that. What about delete from users? All of them gone, right? So always use where on these. So even delete from users where true, delete from users where 1 equals 1. Those are ways to make sure you're putting a where in there, but still being very explicit about what you're trying to do. For the most part, you're actually trying to target a user, though. You're trying to say update user set password equals 1, 2, 3, 4, 5, 6, where user ID equals 72. That's usually what you want to do. Someone in a previous cohort mentioned that they actually do if they want to do a delete or an update, they actually do a select first, and then they change it over to become a delete or an update, because at least then, when they do a select, all they do is they read all the rows that they would affect. And so if they get back 70,000 rows, that's a problem. If they get back 1 row, oh good, the query is good. Now I could switch that to a delete or a update, and I'd probably be safer as a result of that. Sound good? Be very careful. All right. We are getting, oh, good time. We're getting close to the end here. Last thing before I let you go, we'll talk about joins. I got 5 joins listed here. And the good news is we don't have to learn 5 joins. We only have to learn 2 joins. And it's actually the first 2. Inner and left outer. Really inner and outer. Before we do this, now that we're joining tables together, I have to disambiguate my column names, right? If I join, let's say I want to get a table, list all the students and their cohort name. If we go back all the way to the beginning, this is kind of what I want my result set to look like. I want a list of students and their cohort names. But we don't have a database table that looks like this because we made it look like this instead, right? So what I'll do is I will actually select star from students, join cohorts on students ID or students core ID equals the cohort ID. So I'm actually going to use a join to bring these things back together. And what I would get as a result is something kind of could look like this. So in that case, I need to know the difference between the student name and the cohort name. And that's why I have to use this dot syntax. So can you imagine students dot students underscore ID, students dot students underscore names, cohorts dot cohorts underscore name? That's why I said it would be redundant if we prefixed our column names with the name of the table. Because ultimately when we get into and we're going to be doing joins. We don't get away from them. When we get into joins, we have to disambiguate. So we have to use this dot syntax for that. Table dot column. So here's an inner join on these two tables. What's going to happen with an inner join? It's going to go through the students table, and it's going to take a look at that cohort ID, and then it's going to look in the cohorts table for a cohort that matches that. And it found one, February 12th. It now adds that to its result set. Now I have one row, Sam Billings, February 12th cohort. And then it goes to the next row in the students table, and the cohort ID is null. So does it find a cohort? It does not. So with an inner join, it ignores it. Does not include that in the result set, moves to the next row of the students table. Number 3, does it find a cohort for that? It does. It's April 9th. That gets added to the result set. That's why we only have, even though we have 3 students, we only have 2 results, because it's an inner join. And an inner join will exclude any result that does not match the on condition. There's nothing null, does not match anything. This condition is not met. So for an inner join, it is not in the, that row is not in the result set. Right? Question, yeah, please. Sorry? So the question is that the only time it wouldn't add it? It's not necessarily that it's null. It's that it does not match that condition. So even, let's say it's 4, and I don't have a 4th cohort. Then that condition does not match, and it does not get included in the result set. Does that make sense? So here we're taking the cohorts ID, and we have the students.cohort ID. And those things will match for the most part. So in the case of null here, it doesn't match. So we don't actually have that, right? In the case if it was 4, it wouldn't match. If it was 72, it wouldn't match. We didn't have that value. So when that condition does not match, then it excludes it from the result set. In every situation where this condition at the bottom does not match. Now, why this is important is because we have an outer join as well, and an outer join, it would still give us that result if it didn't match. So this is the major difference in behavior between the inner join and the outer join, is that in an outer join, we will get all the students, even those that do not belong to a cohort. Whereas with an inner join, we only get the students that belong to a cohort based on that condition at the bottom there. Okay? So this outer join, what's going to happen, we'll start at the top, we'll look at Sam Billings, we'll look at his cohort ID, and we'll find out February 12th is his cohort name. Put that together, it's now joined in the result set. Susan Hudson, cohort ID is null. We look through the whole cohorts table, don't find an ID with null, does not match. We don't find a row for it, but because it's an outer join, we will still add Susan to the table, to the result set. We're just going to put null in for the cohort name because we never matched it with them. We don't have a value for that. So you would find that all those values that would be joined normally would just get set to null when that does not get met in an outer join. And then Malloy-Jenkins, it'll find that one and it'll add it no problem, right? So major difference between the inner and outer join is that it will exclude unmatched results. And it looks very similar. So here, we'll look at this, inner join cohorts, left outer join cohorts. That's the only difference between these two. Inner join versus left outer join. And actually, inner is optional. I don't have to say inner join. I can just put join there. Inner is very explicit, but it's not needed. Same with this. I don't need the word outer here, but there is a new word that I do need. It's left. The left or the right that goes in here is going to tell us, is going to help us determine which of these tables becomes sort of the authority on what the result set looks like. So, as I said here, we're leaving out any results that don't match that condition. We have to actually sort of predetermine what we're going to do in the case that we don't match something here. And that is we want to include it in the result set, but it's students that we're actually going through the whole table for. And the way we signify that is through this left keyword here. You're going to notice there's a join keyword and a left keyword. There's a students table and there's a cohorts table. What side of the join keyword is the students table on? Or, yeah, students table on. The left side of it. So left join, students to cohorts. That's what this is. If I wanted to, I could swap the words students and cohorts around, and it would actually perform differently. We would start with this table going through it, and when we didn't match something, it would still get included, but the result is going to look quite a bit different. I'll actually show you what that would look like if we went the other way. So when we say left or right, it means the table, what side of the join statement, the table that we're using to figure out what our ultimate result set is going to look like. Okay, I'm going to show you an example of this because it's a bit better when we get into that. I'm going to go down all the way to the bottom here. All right. So I will also, while we're doing this, I'm going to show you how I can reset my data. I'm going to actually import some data into my database. Because this, if I run these queries on the database that I have right now, I've got like 192 students and 12 cohorts. It's too much data for me just to show you this right now. So what I'll do is I'll PSQL into Postgres. I'm going to drop database week 4, day 1. And I'm going to create database week 4, day 1. You can see I can run those in the same line because I put a semicolon between them. Now I have an empty database, week 4, day 1. And now if I describe the tables, there are no relations, nothing in here. And I've got this file over here that we're going to use called joins.sql. And what this does is it drops tables if they don't exist. You're going to be doing that as well. Basically, this is I want to clean up. When I run this file, it'll run all these SQL queries in order. So drop these tables, the cohorts table and the students table. Then create a cohorts table, insert some data for me. Create a students table, insert some data for me. And then reset these sequences to be 4 because I've added 3 values into each table. So if we have some time at the end, I'll explain this, but it's a little bit outside of today's scope, I think. So what I want to do is import, so /i bootcamp /joins.sql. So now it's going to run this SQL file and insert all those, create those tables and insert that data for me. It didn't drop any tables because they didn't exist, but the reason I put that in there is I can just keep running this, and it'll keep dropping and adding those tables for me. Whereas before it would say, I can't create that table, you already have it. So that's why I have to drop at the top of the file. Okay, now \GT, I've got cohorts, I've got students, select star from students, select star from cohorts. And you can see here Susan has no cohort ID. So if I run this query, select ID, name. Oh, and this is another thing I didn't tell you. I can use this as keyword to rename these columns if I want. I'm saying here I want the student's name, students.name as student_name, and I want the cohorts.name as cohort name, so that in my results, when I actually see them, I'm getting student name and cohort name as the column names instead of name and name. Okay. So here we go. With my inner join, it left out Susan Hudson. All right. But the one that we want to actually check out is this outer join. So I'm going to do this outer join, a left outer join. I could say left join or left outer join. Those would mean the same thing. I could say join or inner join. Those would mean the same thing. But the reason I need left is because I need to tell it which table to prioritize for me. And so I'm saying students is the priority. It's on the left side of the join. And this is the results I get back. It did not exclude Susan even though there was no condition met on that join. Now, if I go in here, I have two options if I want to change the way this query is written. I can put right here instead. Now which table is on the right side? Cohorts, yeah. So it's going to be a different result. Because now, oops, my bad. Now, we're going to start here and say I have this February 12th table, or February 12th row. Do I have any students where that condition is met, that this ID matches their cohort ID? Yeah, I do. It's Sam Billings, so we put that in there. And we go to March 12th. Do we have anything where cohort matches 2? No, we don't. But we're still going to include it, and we're going to put null for the name, the student name. And then here, yeah, we have one that matches, so that would be the same as well. So this is going to actually look pretty close to the same, except now we get all the cohorts, but we do not have the student there that didn't have an ID. Okay? And all I did there was switch the right and left. So I told you we only need to learn 2 types of joins, right? But I've just shown you 3. You don't need a right join. Because if you want that behavior, just swap these tables. If this is really what you want, you can still use a left join, just swap the order of those tables. We get the same result, right? So as far as we can tell, a right join is added for completeness, but it's not necessary. And that's why I say you only need to learn an inner join and a left outer join, because you can do the right outer join stuff by swapping the order of those tables. Yes? No, because then it doesn't know which side should be the one that you're starting with, that you're taking those values from, and is the authority, right? In this case, if I want to do a query that gave me all the students that were in the program, not just all the students that were in a cohort, right? That would be how I could do that. With an outer join, I'd have to, yeah. But I have to tell it's the students table that is deciding what is in the final result set, or the number of rows that are in the final result set. All right, there's a couple other things in here. I'll quickly go through that. So right outer join, like I said. Oh wow, that's a bug no one's told me about. Let's fix that quickly. No, that's going to be a bad thing to search in an SQL notes. Let's go to the bottom. Cohort students. So if we wanted the same result above with a right join, we would need to alter the cohorts and students. Yeah, so students on the right side of the join, cohorts is on the left side of the join. I think that's all I need to do there. Yeah, swap that around. Good. Okay, there is something called a cross join. Gives me the Cartesian product. I mean, I don't know of a reason to do this. I mean, it's giving me nine results. I got 3 cohorts, 3 students. So it gives me essentially, yeah, 9 results for that. I could do the same thing if I just said select star from students cohorts. Get the same kind of deal. Okay. So what if I do this instead, where I'd say from cohorts and students, where the cohort ID matches the student ID? Gives me a inner join. So we would just use inner join for that instead. And cross join, I can't think of a situation where we want that. There's also something called a full outer join. I guess you don't need to say left or right in this case, but you still have to put full down there. And then it uses both the tables to figure out It's basically given us both results there that we had before. You don't. This is all kind of just like outside, and you don't need it. You don't need it at all for this midterm stuff, especially. Learn inner joins, learn left outer joins, and all the web database stuff you need to do is at your fingertips. All right. So, any questions this afternoon? We're definitely going to be going through more complex queries and learning about that. That's the goal. You'll have some practice this afternoon, and then if you have questions about what you were doing today, you can definitely bring that. How do you feel? I know it's a lot to take in. Okay. I'll send the notes out. And thanks, everyone. I'll see you at 3.